Right. Well, that gives me the opportunity, till the slides are up, to thank you for the invitation to this conference, and I'm happy to show you in a second what we or how we see Phobos, and mainly Phobos, by the HRSC. There we go. And what we did with this data, basically the image data. This is one example already how you see Phobos with the HRSC, but let me go through the slides. So this is a short overview and some eye candy here at the beginning. This is Mars over Phobos over Mars, of course, and some close-ups here. I'll give you a short introduction on the techniques that are applied in the cameras, and then what we did. And this is basically already a good summary. What kind of information we receive from this data. So the HRSC, as probably most of you or many of you know, is a line scanning camera, especially the part here with the squared bevel. It's operating like this and gives us the opportunity to obtain stereophotogrammetric data, image data, during one flyby of Phobos. Though it was designed for the Martian surface, it's very well suitable for the Phobos observations. The other one additional channel here was added shortly before launch, so to say. It's a super resolution channel, and this is a frame sensor behind that that actually captures or that actually magnifies the scene of the HRSC by a factor of 4 about. And that's why we use a lot of this image data to actually do our analysis. For Deimos, though the title holds the Deimos also, but this is about what we see on Deimos here, and this should be actually a video. Maybe it starts when I go a little bit. Oh. Could the assistants please go one back and start the video? It worked when we tested. So this is basically what we see of Deimos, and usually you should see it dancing here together with Phobos across. Which would be the so-called mutual event. So we see two different planetary objects moving through the field of view of the SRC here. So this, if you adjust, you would see that these images show all this one side of Deimos, basically. Don't worry. And this is due to the highly elliptical orbit of the Mars Express spacecraft that is carrying the HRSC camera, that reaches out to about 11,000 kilometers. This should also be an animation, but never mind. And this pericenter altitude here is optimized above the Martian surface, but then eventually intersects the Phobos orbit, but not the Deimos orbit. So we also we only see Deimos from one side. But Phobos, as already mentioned before, can be seen every 5 months. Oh, there we go. From close range, and we get down to distances below 100 kilometers, whereas the very close distances are dedicated to radio science and not to imaging anymore, because you would have enough smear in there, or too much smear. So for Deimos, we use only far distance observations, but these are used for astrometric observations. And this is here one occasion where you get very close between Phobos and HRSC. So astrometric observations, we have several types of observations, as you can see here. So these are very close range observations with the SRC. And to be able to reduce these, we actually use control points to derive the center of figure of Phobos. Before we used here this limb fitting technique, where we started off with fitting in the triaxial ellipsoid to the image, and now are using the shape model, which I will talk about a little bit later, to fit to the image. And these mutual events are actually not only Phobos and Deimos, but we have Phobos and Saturn, Phobos and Jupiter, and all different kinds of combinations. And here, as we have then a bunch of like hundreds of images during one observation, we actually start modeling Phobos as we see it, and this is a simulation, that's the observation, and then the simulation is rescaled for better fit in the images. So all this information is actually provided to orbit for orbit determination and orbit modeling to JPL and to Valerie Laney at IMCC in Paris, basically, to actually improve the orbit models of Phobos. And they have very much improved during the mission lifetime of HRSC. And we use these results of this orbit or modeling to actually go through this kind of analysis to revise the control point network, improve the shape models, and then do some further analysis, like looking at the moment of inertia, and then compare our observed forced libration amplitude to the modeled forced libration amplitude, which could give you clues on the interior of Phobos. So the control point network, these are kind of old dates, and we are now lucky to say that we have funding to actually revise this work again to include all new data that we have. So this is basically based on 2010 work. So we have SRC images covering 85% of Phobos. Now it's covering all the area. And to complete this work, we actually used Viking orbiter images that were very useful in this at this stage. And we retrieved a control point network all over Phobos with some bigger errors in this area where we included Viking data. But this work actually is used as a reference for all different data sets that we apply. And we use this also for shape modeling and to actually derive spherical harmonic function parameters, coefficients, and also to observe the forced libration amplitude. So this proved to be quite a valuable data set already, but we went on and used then actually the line scanning data to derive a complete set of surface models. And you see here, this is a list of different flybys that we have with different distances from the surface of Phobos that indicates you already that we have very different resolutions in the images. And just to give you an example how that looks like, this is one flyby and this is a different flyby. And what you see here are the different channels on the different viewing angles. It looks as if Phobos would turn underneath the camera, but it's just the different perspective you're looking at the body. And with these image data, with one of these rows, we would create a patch of a DTM patch of a very small area on Phobos, and we do this for all like 20 flybys, and then basically put together the jigsaw puzzle to get a complete global mosaic, global DTM of Phobos. And here you see these are the biggest difference in resolution. So here you have almost 90 meter per pixel, and here you are in the order of 4 or 5 meter per pixel. And we use all of these data, otherwise we couldn't complete this entire DTM. You see there are a few gaps that are filled then again with Viking images, image data. And this is a representation of the gridded DTM. So, and we can actually say we have very good data in the north, medium data in the south, and relatively poor in this area because HRSC wasn't able to really observe this area. This is the first opportunity we have is in 2018 when HRSC will be able to see this area under good illumination conditions. This is something that Daniel already showed this morning. These are the shape models. So here, in comparison, this is the DTM as a 3D display and the spherical harmonic function model. And then we use this, of course, for cartographic products or here the dynamic studies by Shisian et al. That actually looks at the dynamic heights and the slopes. The slopes are actually, that's also something Daniel mentioned this morning, something that we looked at. We looked at here the deposits on Phobos, and this geometrical or topographic height here or slope is too shallow to explain this deposit. But if you look at the dynamic slope here, this would be Phobos moving outward to a greater distance. So here the tidal effect of the tidal forces of Mars do not show a big effect. But then if you move it to the current location, you have a much steeper slope here. And this dynamic slope is actually then just above the angle of repose, and then you can explain these deposits here. And this is something that we're currently writing up for publication and should be submitted in the near future. Oops, sorry. Other applications for the shape models are to derive the bulk properties like volume and bulk density. Bulk density, of course, together with the findings of radio science from close flybys. We have increased the accuracy here mainly. This very well corresponds also to the early Duxbury and Callahan publications from the Viking data. No, doesn't go on. And I already mentioned that we have observed the forced libration amplitude. This is basically an empirical derived method where we change the amplitude and then look at the residuals of our computations. But now we actually implemented one functionality that we can directly solve for the forced libration amplitude, and we resolved to about -1 degree forced libration amplitude, which agrees to also work done by our Russian colleagues. And you could now go and compare these two, and then try to fit like simple models. Pascal did this with random elements, and you see that if you have different layers with different densities, you get very close to the observed and the modeled amplitude. We did this before with different values, basically agreeing on a very high porosity inside of Phobos. This is just a sketch of our cartographic work. We have different map sheets if someone is interested. We also provided this publicly to PSA. I heard that PSA and PDS is not syncing very well at the moment, so it might take a while till it gets to the PDS archives, but it's on PSA archives already, and you may actually get hold of all the data that we produce based on the HRSC data from these locations. So just a quick outlook at the end here. The mission, the Mars Express mission, is actually confirmed to 2018, and currently we are preparing everything to get another extension to 2020. 2018 will be actually also the first opportunity to observe the anti-Mars site with Mars Express and HRSC. Observation planning for the imaging data is on improving the stereo data and the coverage by the color channels of the HRSC. I didn't mention the color channels, but there are also quite a lot of color images of Phobos available. We also are currently finalizing our paper on the mutual event observations to further reduce this astrometric data. And as already mentioned, we are now received some funding to actually work on this new data and refine further the shape models and control point networks. And I'm happy to share this data with everyone who needs it. As already mentioned, it's published to PSA, so PDS should be not far behind. And that's some eye candy for the finish. Thank you.
We have time for one question.
I'm sorry. That was too long.
Thank you very much.
Yeah.